In this video, we introduce the concept of sequences and a special type of sequence called arithmetic progression. Now, a sequence is a listing of terms in a defined order with a rule for obtaining the terms. Consider the following list of numbers. Which of the lists is a sequence? Now, if you observe the first list, you can easily see that from one number to the next, we add 4. For list number 2, from one number to the next, we subtract 6 all the time. For list number 3, from one number to the next, we always multiply by 2. And for list 4, when we study closely, we observe that from the first number to the second number, we add 2. From the second to the third number, we add 4. From the third to the fourth number, we add 1. From the fourth number to the fifth number, we add 2. We don't see a fixed pattern in the numbers that we add from one term in the sequence to the next. Thus, the first 3 lists are sequences, but the fourth list is not a sequence. The first 2 lists, in which one number is linked to the next number by the addition of a constant, we call such sequences arithmetic progressions. For list number 3, whereby each number is linked to the next number by the multiplication of a number, we call such a sequence a geometric progression. When we talk about sequences, we are interested in finite and infinite sequences. Now, what are finite and infinite sequences? Look at list 1 and 2. You observe that we indicate dots after the last number. These dots indicates that there are more terms following, which means that we really don't know the total number of terms. The number of terms are infinite. Now, when we look at list 3 and 4, we do not see the presence of dots. The dots are absent, indicating that the numbers 90 and negative 22 are the last terms. In list 3, there are a total of 5 terms. Similarly, with list 4, we only see 5 terms with negative 22 being the last term. Thus, lists 3 and 4 are what we call finite sequences. In summary, lists 1 and 2 are the infinite sequences with infinite number of terms. Lists 3 and 4 are finite sequences with only 5 terms each. Next, we'd like to introduce the term arithmetic progression. An arithmetic progression is a sequence of numbers in which each term is obtained from the preceding one by the addition of a constant number called the common difference. Let's revise the 2 of the lists that we have seen earlier, 2 of the sequences that we've seen earlier. Now, in these 2 sequences, we see that every term is linked to the next term by the addition of a constant number. In the first sequence, we add 4 all the time to proceed to the next term, and this 4 is what we call the common difference. Now, in the first sequence, we see that the first term is 3. For the second sequence, we see that we proceed from one term to the next by the addition of negative 6, or we say we subtract 6. The common difference here is thus negative 6, and the first term u1 is 2. How do we denote the general term of an arithmetic progression? Now suppose the nth term of an arithmetic progression is denoted by un, meaning we use u subscript 1 to denote the first term, u subscript 2 to denote the second term, u subscript 3 to denote the third term, and so on. We would also like to call the first term u subscript 1 as a. Now, since we know that from the first term to the second term in an arithmetic progression, we add a constant called the common difference d, we will say the second term is actually the first term plus d, which is a plus d. Now from the second term u subscript 2 to the third term u subscript 3, we again add the common difference d. Thus, the third term is a plus d, meaning a plus 2d. From the third term to the fourth term, we add the common difference d again, and thus the fourth term is denoted by a plus 2d, add another d, which gives us a plus 3d. If we continue this process, we'll wonder, what if we have the nth term u subscript n? How will we denote it? Now, to do that, we will need to study the suffixes of each term carefully. For example, in the fourth term, u4, the suffix is 4. Now, let's compare to a plus 3d, the number 3 there. Do you see a pattern? Do you see a relationship? Now, let's analyze the third term u3. Subscript is 3. When we compare to a plus 2d, which is the representation of the third term, we compare the 3 and the 2. What do you see? Next, if we analyze further the second term u subscript 2, and we compare it to its representation, a plus d, what do you see between the subscript 2 and d? We see that the number of d's added to a for each term is exactly the subscript number subtract 1. Therefore, for the nth term un, since the subscript is n, we say un is a plus n minus 1d. That's the end of the recording.